Yeah, so number one on the practice piece of paper is one of these cool angle problems. It says the center field fence in a ballpark is 28 feet high. So that's way out here. There's this 28-foot tall fence. So by the way, that's kind of 28 feet tall fence there. And that's the center field fence. It's 390 feet from home plate. So that's X kind of. It's 390 feet from home plate. The ball is hit at a height of 3 feet, which is kind of how a baseball is hit, about 3 feet. This guy hits this baseball, and we want it to barely be a home run. You know what I mean? We want it to barely clip the wall. So in other words, to be a home run, it goes over the wall, and that means when X is 390, we want Y to be 28. I mean, that's kind of what this problem comes down to. When X is 390, we want Y to be 28. Now, it also told me that it left with a V naught of 100 miles per hour. Well, I need to change that to feet per second. Can you help me with that? How do you multiply by, let's see, 5,280 feet, 1 mile, 36, or 1 hour has 3,600 seconds. This is how you do it, you guys. I need this.
146.67.
146.7 feet per second. Okay, thank you. That's the V naught. And the question ultimately is, I'm just talking so much I didn't get to the question. The question is, what's the angle? What angle? And actually the question is, what's the minimum angle? Guess what? That just means there's probably 2 angles and pick the smallest one. There's usually 2 angles to hit a given spot. And we want X to be 390 and Y to be 28. And so I got my projectile motion thing memorized. You don't have to have it memorized. I'll write it up here again though. It's V naught cos theta t for X and H plus V naught sine theta t minus 16t squared for Y. That's kind of the way we structure it. Yes?
Isn't the other angle just going to be the original, or 90 minus the original angle?
Good question. Let's see what happens. You might be right. I mean, let's find our 2 angles. But you're right, they might be complementary. He thinks they're complementary angles. We'll see. Let's see what happens. Do you think they are? Anybody else think they are? Okay. All right. Now, what am I going to do? Oh, I said it. I already said it. When X is 390, my Y has to be 28. I mean, that's what even though I have this one equation that talks about the motion of this baseball, I really take it apart and analyze it in pieces. And so the 390 is going to be the X, and that's the V naught, the 146.7. Cos theta, I don't know theta, so cos theta times t. I would divide and call this t is, I'm going to solve for t here, t is 390 over 146.7 cos theta. And actually, I'm not even going to pick up my calculator quite yet. That's t in terms of theta. What about y? I want y to be 28. Yeah, I want y to be 28. And what is h?
The initial height.
Which is?
3.
That's my 3. That's my 146.7 sine theta times t. But guess what I'm going to do? I'm going to substitute in that t for this t. So that t is 390 over 146.7 cos theta minus 16 times t squared. But that I'm going to plug that t in there. 390 over 146.7 cos theta squared. And then I got this game down, man. I got this game on how to solve for theta. I mean, we solved for t, substituted it in for that t. My only variable is theta. And I know how to play this game. I've played it for years. Do you know how to play it?
Yeah, I use trig.
Tan theta.
Well, we're going to call this tan. You're right. Over here, I got a cos squared in the denominator. A cos squared in the denominator is secant squared. I'm going to change secant squared to 1 plus tangent squared. And so I'm going to end up with a quadratic equation with tan theta as my variable. Right? A quadratic equation with tan theta as my variable. That's where this goes, in case you want to hear the big picture. Let's work on the details. What's cool about this is the 146.7 cancels. And you get, let's see, I'm going to move this 28 over here. Negative 25 and 390 tan theta. Right, you guys? Mm-hmm. Cool. Over there, I'm just going to divide and get myself a number. It is 390 divided by the 146.7, and then whatever that is, it's squared, and then it's times 16. So it is 113.08, negative 113.08. That's that coefficient, and it's over cos squared, but I'm going to call that secant squared, and if you don't mind, that's 1 plus tangent squared. So I skipped a few steps there, but cool. And then I distribute the 113.08. The truth is now I like to move everybody to this side because I want, so it's a positive 113.08 tangent squared theta. Well, it's negative, and then I added it over here. This 390 is coming over here, so it's negative 390 tan theta. And the only other thing left over there is the negative 25 and the negative 113, which is negative 138. But then I move it over here, so it's a positive 138.08, and this equals 0. I think I did that right. And now I'm doing a quadratic formula. Tan theta is the answer to the good old quadratic formula. All over 2a. So if we do the quadratic formula, we get 2 decimal answers here. This is the tan of theta. I could trust you guys.
Yeah, I got 3.04 and 0.04.
Okay. Can you give me more decimals?
3.0483.
All right.
0.40057.
Point
4.
0.4.
0057.
0057, 006. So those are the 2 numbers that are the tan of theta. And now if we hit tan inverse of those numbers, we'll get theta. We should be in degree mode. I think I want a degree here. I trusted him on those numbers.
That's not what my calculator's kicking back to the right side there, but I don't know if I trust my calculator.
I haven't done tan inverse yet. Those are just the numbers before tan inverse.
Yeah, I don't know. Yeah, the right side can't be this simple because the radicand turns out to be greater than 226.16.
So I got a 3.0483. I got one of these. This plus this over this. And then I have this minus this over this. 390 minus whatever that was.
Okay, so wait, I think that might be why I'm getting something different because I'm getting 1.7244 blah 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 blah. Plus minus 1.323, etc.
0.40057. Yeah, I like these 2 numbers. I agree with him. So you shouldn't get anything different. You should do a good quadratic formula. Be careful. Do it slow and steady. Yeah.
crazy.
Well, I mean, I would do this. I would do all this work, and then take a square root. And I did that, and I got 299 point something coming out of this square root. So now I got 390 plus or minus that over this, so.
I'm getting that coming out of the square root.
Okay.
Divided by 226.16.
Well, hang on. I mean, you should add them before you divide, maybe. I mean,
Okay, so
depends on how you're
I
gonna.
think I'm getting the radicand right. How are you getting to the number from the bottom
Right.
once you've simplified the square root term?
Okay, so the square root turns into this.
Yes.
So now there's, look, so then it's this plus 390 over this,
Okay.
or this subtracted from 390 over this. Right,
Okay.
that's the last two steps.
Yep, got it.
Cool. I'm gonna hit tan inverse. Well, I'll let you guys. You guys hit tan inverse in degree mode, you give me two angles, what are they?
71.8 and 21.8.
All right, cool. Cool. So we're done. They wanted the minimum angle, so we'll toss out the big one and just give them the small one. I mean, this guy, when he hits this ball, he has two chances to hit a home run. The high angle shot or the low angle shot.
I think that's something we talked about in physics too. What's the maximum horizontal distance you can switch it? It kind of reminds me of that.
Right, there's always two angles to get to a certain spot, unless it happens to be max distance. Then I think the only way to get there would be with a 45-degree angle, I suppose. But that also might only happen when you're at the same level.
Oh,
Go
yeah,
ahead,
you're
what
right.
do you want to say?
Figured out what I was doing wrong.
Okay.
It's not a plus minus there between 3.0483 and 4.006. That's an and.
Right. There's a plus minus, right. Right, I was getting the answers to these, right, please give me the answers. Thank you. Cool. There's two answers and there's two angles, and notice something, they are not complementary, Zachary. They're damn close though. I mean, 70 and 20 would have been 90, but 71.8 and 21.8, they're not quite complementary. I mean, they're not quite complementary. Do you know why? Do you wonder why did you think they would be complementary, and how come they're not, or should they be, or what anybody got any thoughts?
Range. That's what I was thinking. I mean,
Yeah, that's a word. That's not much of an explanation. What do you mean?
well, I mean, in physics, there's range equals something I never memorized.
Is it sine 2 theta over g?
Right.
Something like that, yeah.
Sine 2 theta.
All right, anyway, I'll tell you. The truth is, so I'm saying, anytime you want to hit a spot, there's always two angles to hit a spot. There's a low angle shot and a high angle shot. And guess what? Those two angles will be complementary when
When it's
the
at
height
zeros, yeah.
that you shot at and the height you landed at are the same height. Then they're complementary angles. So when there's a little bit of a difference in height, like this was 3 feet and he was trying to get to 28 feet, that's not much different, but it's different enough. I mean, that 3 and 28, that made them slightly not complementary. You know, the other day we did the one in class that had a drastic change in height. I was up on a cliff really high and I was trying to hit something way down here. I mean, it had a big change in height, and the two angles I got were very non-complementary. I mean, they weren't quite close to 90. So the closer that height difference is, the closer it is to 90. And if it's the same height, starting and landing height, then they are complementary angles. They are 70 and 20, or 60 and 30, or 65 and 25, or right. pretty cool.
That's why I thought they were going to be complementary because range is only applies when they're at the same height. I missed the difference in height. Change that. I wasn't thinking.
Yeah, cool. So that was off your practice paper. I mean, it's a good problem. It's a good, I don't know, I like it. So your test might have something like that on there. Maybe some other projectile motion, I don't know. There's one or two on your take-home quiz. What about, have you guys been, any homework you want help with? 12.4, 12.5, I got into this curvature and stuff. I haven't done much with it. Let me see. All right, here's something. There's this number 54, so I just jumped into 12.5 here. And there's this number 54. Keep in mind for Friday's test, you don't need to memorize tons of formulas. I guess you need to know that sine over cosine is tangent. You need to know secant squared is a 1 plus tangent squared, and 1 over cosine squared is a secant squared. I mean, I don't know, I guess there is. But these chapter 12 formulas with velocity and curvature formulas and all that, I'm going to give you. So what did I do? I found a problem here in the book. 12.5, number 54. The function is y equals e to the x. Nice, cool, old function there. And they're asking me all about the curvature. They're saying find the point where the curvature is a maximum and also find the limit as k goes to infinity. So there's two questions here. I mean, I'm sorry, there's two questions. They say find the point of max curvature, maximum curvature. And part B, find the limit of the curvature. Well, I'm writing it like this. As x goes to infinity, I'm writing it like this. Well, I said you don't have to memorize these formulas, but there is this curvature formula, and there's several curvature formulas. You can look them all up in the section 12.5. But there's this one that kind of goes with when you have y as a function of x, the curvature formula is this. The absolute value of y double prime over 1 plus y prime squared, all to the 3 halves. So you don't have to memorize it. I do. Feel sorry for me. But that's a nice formula for curvature. So I'm going to do it. I'm going to try to find a curvature function for this. Okay, well, I guess I need y prime and y double prime. Can you guys help me? What's y prime?
E to x.
What's y double prime?
E to the x.
Okay, cool. So here I go. The curvature at any x then is this. It's the absolute value of e to the x. I'm sorry. Is that what's y double prime? E to the x?
Yeah.
So it's the absolute value of e to the x. The truth is that's a little redundant. It's very redundant. E to the x is always positive. So putting absolute value on it is a little unnecessary just because an e to any power is always positive. So I can remove those absolute values. Over 1 plus y prime, which is e to the x squared, all to the 3 halves. All right, so if I wanted to just simplify this, I can remove the absolute values. Not really much I can do down here, except e to the x squared could be called e to the 2x. So this is sort of my simplified curvature function for this curve. You know, this is such an easy question. No, this is not that easy of a question. This second one is. Can we skip A and go to B? Now, they wanted to know the limit of the curvature as x goes to infinity. Now that I've got a curvature function, maybe I can sit here and talk about the limit as x goes to infinity. The truth is, that wouldn't be all that hard, but let me show you a different approach. This is, what we're talking about is this e to the x function. This e to the x function looks like this. You should know that it gets very steep and keeps, and so as x goes to infinity, it's super, super steep and looks very, very straight. When x goes to infinity, this thing is super straight, super steep, and super straight. So how curvy is it? It's not. And so as x goes to infinity, what do you think the curvature is doing on something that's very straight looking? As x goes to infinity, the curvature goes to zero. You know, I never officially said this, I guess, but the curvature of a straight line is zero. And this is not a straight, and by the way, I didn't mean to say horizontal line, I meant the curvature of a straight line is zero. And this ain't a straight line, but god dang. Hey, this is not a straight line. Look at it. Please look. That's not a straight line. But it sure looks like one. I mean, it's got a little curve to it because it's an e to the x curve, but god dang it, it sure looks. So as x goes to infinity, this thing is getting very straight, and I would say that the curvature function goes to zero. And I did that just based on this picture. You know, I would say the same thing, you guys. I would say the same thing about a parabola. I mean, look at this. I mean, as x goes to infinity, what's the curvature going to do? I mean, I think you're on this parabola, and you're going to be on this leg of the parabola, and it looks, I mean, when you're way out to infinity, there's nothing too curvy about this parabola. It looks awful damn straight, and I think the curvature goes to zero. It's probably true on a lot of things. I mean, what else could I draw? Probably not a sine wave. A sine wave keeps curving. It never really straightens out, right? But, you know, I don't know, a log function? When x goes to infinity, that log function looks awful darn straight. I think the curvature goes to zero. I mean, right. So, I answered this easy question first, and I did it my easy way. I tried to explain just conceptually. Dude, the function is straight. His curvature goes to zero. I mean, I tried to explain it that simply. You could look at this. As x goes to infinity, you get infinity over infinity. You could talk about L'Hopital's rule a little bit. But, you know, the truth is,
Bigger infinity on the
it's a bigger infinity on the bottom. Now, how do you know that? He's e to the infinity. He's e to the two infinities.
plus 1.
But he's being square rooted. Yeah, plus 1's pretty insignificant. When you head to infinity, the plus 1 is very insignificant. As a matter of fact, you could forget it for a second. It's e to the 2x, and then he's square rooted, which makes him be e to the x. But then he's cubed. So my numerator is like an e to the x, my denominator is like an e to the x cubed. So when they both go to infinity, zero. The denominator goes to infinity quicker, that's 0, right? So you can approach it like a limit problem, or you can approach it with common sense. Back to this question. How do I find the point of maximum curvature? Well, I'm not maximizing the function, I'm maximizing the curvature function, which is this. Do you know how to maximize something? You're calculus students. Do you know how to maximize something?
Set the derivative equal to 0.
Take the derivative, set it equal to 0, Does anybody want to do that? Say no.
No.
Yeah, I kind of don't either. I mean, this derivative would be pretty rough. It's doable. You're calculus students. You should have said yes, I guess. You did want to do it, but yeah. So on a question like this, and if this is on my test Friday, okay, anyway, or here, what I expect maybe is to come up with this curvature formula, but then maybe use your graphing calculator to find out when it's a max. So I'm not really asking you to analytically prove when this is a max. I'm asking you to find this, and now, can you graph him? Can you graph him, the curvature function? So now you're typing this in your calculator. I mean, that's an exercise in itself. Maybe you would rather do the derivative. But you could type this in your calculator and try to graph the curvature function and use the maximum minimum feature on your calculator to find out when it's a max. Can you actually do that? I got to get back to function mode. I got to go to y equals. I'm going to try to type this in. I'm going to type in e to the x. Oh my God. I'm going to type in e to the x. I'm going to type in, try it for the third time, e to the x divided by, parentheses are important down here, a 1 plus e to the 2x all to the 3 halves. Can I just say to the 1.5? Maybe I can. And I'm going to hit graph. And I see nothing. I mean, I see nothing. I think my window is -20 to 20, -20 to 20. I'm going to go to zoom decimal. I like zoom decimal. That's a nice tight window. And oh, now I see something. Dude, this is the little curvature function I see. Do you guys see it?
Yeah, it's kind of small.
It's just, I see a little, so this is the actual function, okay, the e to the x function, and here comes the curvature function. See that? So when is it a max? When is this little curvature function a max? Probably right about there. You with me?
Yep.
Somewhere right there is a max, which maybe, when is this e function the most curvy? I mean, it's kind of hard for us to tell, but apparently right in there is when it's most curvy. I mean, I got them laid on top of each other here, but now it's getting messy. But the maximum of the curvature function, and I'm now going to actually use the calculator to find it. You guys know, I don't know if you know how to do this. You go to second, calculate, and there's a button called maximum. It wants me to get on the left side of where I think the maximum is, so I move to the left, I hit enter, it's asking for a right bound, so I move to the right, I hit enter. It gives it a guess, they want to guess, so I just hit enter. It looks around in between there and tells me that the max occurs when x is, max curvature happens when x is, did you guys do this? -0.346, something.
Yeah.
That's what my calculator said.
I took the derivative. I think I took the derivative. Actually, could you take the derivative of it? Because I'm not
Well,
sure that
I might want to work on some other problems.
Okay.
But someday I might. Yeah.
what you do is it'd be e to the x times the derivative of the bottom minus the derivative of e to the x times the bottom all over the bottom square.
I guess so. You could do a quotient. Yes.
Okay. Or you could raise it uphill.
Yeah.
Product rule, I guess.
Yeah.
Then there'd be a lot of factoring. I didn't know so much using my calculator anyway.
You guys use your calculator? That's probably it, maybe.
Maybe I have to just.
It's like the one you had.
You could go to your window. Hit window. Yeah. See, I had a little. That's probably it, though. Go to zoom. I went to that zoom decimal. See that zoom decimal window? Hit that. It's just a tighter window. It's negative 4.7 to 4.7 or something. Still looks like ours, I think. Now, can you use your maximum button? Do you know how to do that?
No.
Go to second, calculate, which is there. Yeah. There you go. That's all the good stuff's in there. So there you go. And then you got to get to the left. Move over to the left and hit enter. Kind of the left of where you think it is. Hit enter. Then get to the right of where you think it is. Hit enter. Then just give it a guess. So just hit enter.
Um, 0.346.
Woohoo! That's what I got. Good job.
-.3465,719.
All right, let's do something else. What about this curvature question? Here's another curvature question here. It just caught my eye. I assigned you guys 35. I like the looks of 35, but I won't do it. Let me try, I wonder if I could try 32. A cosine omega t, B sine omega t. This might be terrible. They're giving me a vector valued function, and here it is. A sine omega t, comma, B, no, I'm sorry, hang on. A cosine omega t, B sine omega t. This one was cosine. Yeah, I kind of like when they sine omega t. They do this stuff kind of in general. This could be rough. Why do I think this could be rough? Do you know what that is? Do you have any clue what that is?
There's a circle.
Good. I mean, it's your good old circular motion, but it's cosine and sine. It's your good old circular motion, but wait a minute. It ain't a circle. Why not?
Because of A and B.
Because A and B are different. So what is it?
Ellipse.
It's an ellipse. Right, okay. So my first thought is it's circular motion, then the A and the B are different, so no, it's an ellipse. And man, anytime, I mean, ellipses just, circles are nice, ellipses are a little worse. Because the coefficients aren't matching up, the computations get a little different. And by the way, I guess there's no numbers here. This is just an ellipse centered at the origin. You know, depending on whether A is bigger than B, it's just, that's what it looks like. It is traveling this way. It's got a period of 2 pi over omega. Anyway, you know, but what do they want? They want the curvature. Good God. Just in general, not at any point. They just want the curvature. Well, look, we just did a curvature problem. When you have y as a function of x, this is your formula for curvature. When you have y, you know, good old y equals f of x. But now that you got r of t, what's our formula for curvature? Well, I don't quite have that one memorized. Again, you don't have to have it memorized either. What the hell is it? It's in here. If I have well, I got a lot of options. I got a lot of options, you guys. Here they are. One of them is t prime of t over r prime of t. T prime of t magnitude over r prime of t. magnitude. Okay, I could do that. Or I could do this, r prime of t cross product r double prime of t magnitude over the magnitude of r prime of t cubed. Look at this. Apparently, you know, there'd be a nice proof in here of trying to prove how this is the same as this. Apparently these are the same. There's a third one though. Here's a third one even. A dot A of t dot n of t all over v of t squared. Good God. A of t dot n of t all over v of t squared. Huh. Oh well, I don't know, dude. I mean, which one? I kind of feel like doing this one. Maybe you guys don't agree. I mean, I don't want to do this one because I don't want n. N always. I mean, I remember I did some problems the other day. And n was the hardest thing. T wasn't all that bad, of course, but this is t prime actually. But n wasn't too fun. You know, I don't know. I'm sort of tempted to just try this. So I just need an r prime and an r double prime, and then I got to get to work. What is r prime? It's not. What is r prime? Do you know how to do a derivative? You know it's going to spit out.
So negative a or negative a sine
AW, sorry.
AW, yeah, negative AW sine omega t.
Good, because it spits out, the chain rule spits out that omega. And then b omega cosine. And I like these sines and cosines, but when their coefficients don't match, it ain't as cool. It ain't as cool. Let me try r double prime. What's r double prime? Negative a omega squared cosine omega t. And then b omega squared. Wait, negative. Derivative of cosine is negatives. Negative b omega squared sine omega t. And so then I'm going to try to do a cross product. You know what's funny is, you know, when we do cross products, they were always 3D, and these are 2D, but they can be thought of as 3D. I mean, what is the z component? 0. So I can set up a cross product. What did you want to say, Zachary?
I was just going to ask if we had to memorize the formulas for t and n.
No.
Okay.
So what am I doing? R prime cross R double prime? R prime. Good Lord. Hang on. I need to make this bigger. R prime. Negative a omega sine omega t. B omega cosine omega t. You guys like doing all these in general like this? Negative a omega squared cosine omega t minus b omega squared sine omega t, comma 0. And here's my I, J, K. Okay, so now I'm doing this cross product. Okay, this is going to be so much fun. All right, this part is fun. Ready? You do the I guy, and to do the I guy, you cross that out. You do this: 0 minus 0. Good job. Comma. And now you cross out the J guy and you do this. 0 minus 0. Zachary. Good job. And then you do this guy. This, which is a positive, AB omega cubed sine squared omega t, isn't it? Is that what it is? Minus this guy, which is a negative, so it's going to be plus AB omega cubed cosine. Dude, this is working better than I thought. What is that?
staggering identity when you factor out the ABW.
You do. You factor out the AB omega cubed, and you're left with sine squared plus cosine squared, which is 1. So this is AB omega cubed. Wow. That is the fun of doing it in general. It works out. That's this. And that's my cross product. And now what am I going to do with that cross product? What am I supposed to do with this cross product? Find its magnitude. What's his magnitude? If it was 0, 0, 6, what's the magnitude? 6. If it was 0, 0, 12, magnitude's 12. So what's the magnitude? It's that number. So it's that number. Cool. Dude, this is awesome. So it's that number, AB omega cubed, over, what's it supposed to be over? Oh, R prime, oh, the magnitude of R prime cubed. This might suck. Yeah, I think this sucks. The magnitude of R prime. I mean, here's my R prime.
Can't you do the same thing as the other one?
Well, it ain't gonna work out. I mean, because those coefficients, this worked out, this cross product worked out nice. This is not gonna work out nice. I just need the magnitude of R prime. Of course, the magnitude of R prime is, you know, it's the square root of that dude squared. So A squared omega squared sine squared omega t plus the other guy squared, which is B squared omega squared cos squared omega t. And you can't really get rid of those sine squareds and cosine squareds, can you?
Could you, oh, no, you can't.
You can't really get rid of those sine squareds and cosine squareds because they don't have the same coefficients. You want to factor out an omega squared? You could factor out an omega squared, and it would be sitting, wait a minute, you could factor out an omega squared. It's still in the square root. When you pull it out of the square root, it'll be omega. What's left in the square root then? A squared sine squared omega t and B squared cos squared omega t. And because the A and the B don't match, I can't, this is stuck. That's why ellipses are, if it was a circle, it would have been some number. But with this ellipse, it's stuck like this. Now wait a minute, that's my R prime. And now that needs to be cubed. So it's down here and it's cubed. The W gets cubed, I mean the omega. And this nasty square root thing gets cubed. This is kind of cool. Maybe you don't think it's as cool as me, but we just found a little formula for the curvature of any old damn ellipse right here. These omega cubes can cancel. And it turns out the curvature is AB over that square root. You know, it is a square root cubed. I could call it to the 3/2 is what I could call it. But there's really nothing else I can do in this abstract world here. How you guys doing? Yes, sir?
I think you could fiddle with the trig maybe too.
I know.
Oh, it would be fun.
You really can't. I mean, the only thing you could be, with a sine squared, you can make it 1 minus cos squared. And then you could try to group your cos squares together, but they do have different coefficients, so you kind of... It doesn't go very far in her root, so... So, cool. That's the curvature of an ellipse at any moment. That's pretty neat. Now that you got that, you can use it. Anyway, yeah, I like doing homework. I like doing homework. I found that in 12.5. what was that, 32? Yeah, I told you guys to do 35. Okay. I might try something else. I just flipped back to 12.4, and I found this problem 66 that I assigned. It says it's a projectile motion problem, but it's in 12.4 where we learned about t and n and little at and little an, which were the tangential and normal components of acceleration. Let's see what this says. A plane is flying at an altitude of 36,000 feet at a speed of 600 miles per hour, releases a bomb. Releases a bomb. Maybe it's a bomb of peace, you know, somehow. Perfume or something. Releases a bomb. Find the tangential and normal components of acceleration acting on the bomb. Wow. So this plane is flying. This plane is flying up here at 36,000. That almost doesn't matter. It's flying. And but it is moving this way at 600 miles per hour. And then it releases a bomb. Boom. So, you know, it really just drops the bomb. It drops it. But can you tell me anything? Like, I think it just drops it. So, can you tell me anything about the initial velocity of the bomb?
0.
0. Because it just drops it? The initial velocity of the bomb is 0.
So it starts at x.
Kind of.
Oh, no.
Does anybody want to argue with that? I mean, you're onto something, but I didn't. I want to talk about the initial velocity of the bomb.
So that's airplane speed?
Yeah. So I think the initial, now this is out, the initial velocity of the bomb in the y direction is 0 if it was dropped. But I think the initial velocity of the bomb in the x direction is
600 miles.
Thank you, right. It's in this plane moving this way, and so when it gets dropped, it's moving this way. Yeah, it's 600 miles an hour, right. Right. So it's got a bunch of initial velocity in the x direction, but it's got no initial velocity in the y direction when it gets dropped. And so what does it do? Then it follows this parabolic path and lands. I mean, that's what a bomb does. It's got all this horizontal initial velocity that causes it to go this way as it falls. All right, so they're asking me about the acceleration. No, they weren't. They're asking me about the tangential and normal components of acceleration. First of all, what is the acceleration? In terms of I and j, what is the acceleration? What is the acceleration?
0, negative 32.
Thank you. It's gravity, and you just told me what that is. Yes, thank you. What is the acceleration acting? It's gravity. There is no acceleration from the plane. I'm sorry. It's gravity, right? And it's 0, negative 32. Now, hold on. Is that tangential and normal components? No, that's horizontal and vertical components. You know, it's right. That's gravity. So, how much acceleration is tangential and how much is normal? Hang on, now I'm getting confused. So you're saying at any moment on this path, hang on a second. At any moment on this path, I mean, I could draw this little, there's the acceleration vector. There it is, there it is, there it is, there it is, there it is. I mean, it's never changing, is it? It's always straight down, negative 32. So that's the acceleration vector. Now, how much of that is normal to the curve? Oh, and how much of it is tangent to the curve? I mean, that's what AT is. AT is how much of this is tangent to the curve and how much of this is normal to the curve. That's, I mean, there's my T and my N, and my AT is how many of those and how many of those make up this velocity. I mean, make up this acceleration. Okay. So, guess what? That's not as easy as I thought, now that I'm thinking about this, especially after I drew this picture. I think AT and AN are constantly changing. I mean, how much of this acceleration is tangent and how much is normal? I think that's different over here and over here and over here and over here and over here. I think how much is tangential and how much is normal keeps changing throughout this fall. What if we just said we were at the peak? What about, I'm changing this question a second. What if I was right there?
0,
At the peak, how much of the acceleration is tangential?
No.
0, huh? I think you're right. I think all the acceleration is there's no acceleration that way. I mean, that's tangential at the peak. And I don't think there's acceleration is straight down. There would be 0 acceleration in that direction. How much would AN be at this moment? At this moment?
32.
It would be 32. I think I'd call it 32. It's the normal component of acceleration. I don't think I want to call it negative, but it's 32 units in the normal direction, which is on the concave side of the curve. I don't think I want to use the negative there.
So everything, the positive y direction's everything down. Okay.
So all the acceleration is straight down. I mean, we know that. But at the peak, hang on, this is stupid. First of all along this curve, all the acceleration is straight down. There is no acceleration sideways. All the acceleration is straight down. Wait a minute. All the acceleration is straight down. That's true. But you can take acceleration and break it into 2 pieces. How much is tangential and how much is normal? And at different places on this curve, that'll be different. But right here, how much is tangential? 0. And how much is normal? All of it. But over here, maybe there's 12 tangentials and 13 normals. Or, I mean, I don't know. I'm just guessing. Maybe over here there's 6 tangentials and 14 normals. And over here, I don't know. Maybe it's more tangentials over here. So I'm playing around and I'm not really answering this question. Sorry, I'm just thinking and talking about an object. I'm not answering this question. Should I answer this question? Can I write the vector valued function for this thing? Well, first of all, I think I need the 600 miles per hour converted. Help me with that. 600 miles per hour multiplied by 5,280 feet in 1 mile multiplied by 1 hour has 30,600
880.
seconds. What'd you say?
880.
880. Exactly. 880 feet per second. Okay, thank you. So can I write the vector value function? I know you guys don't have this memorized either, but for projectile motion, it was 880 times the cosine of the angle. Look at this bomb. What angle was this bomb released at? You can get yourself confused here. You know, it was dropped straight down. You could say that angle, -90, but that ain't really right. It's this.
It's like standard position.
It's this angle. The bomb was, it was dropped out of the plane, but the plane was moving this way. So the angle it was a 0-degree angle. So what's the cosine of 0 degrees? 1 t. So that's v naught cosine theta t. And then I got this h, I guess that's my 36,000 feet. That's my h. I could put v naught sine theta, but what's the sine of 0? 0. So that middle term goes away. -16 t squared. So this, I think this is it. Was this really 36,000 feet? Is that this? Yeah, 36,000. That's my projectile motion. The sine of 0 was 0 and the cosine of 0 was 1. The angle was 0 degrees. That made this equation pretty nice. Go ahead.
Is there a t on the x part of that?
No? Yes. Yeah. It's v naught cos theta t. Yeah.
Oh, it's the position. Okay, correct, gotcha.
The derivative is the velocity. Let's just check it out. It's pretty easy. 880 and -32t. And the second derivative is, of course, acceleration, which we already know is gravity. I mean, we already knew that. What am I looking for? I'm going round and round and round trying to avoid the issue, I think. Maybe not really. I needed this stuff, I think. I needed these equations because what I'm really trying to find is AT and AN. Now, you don't have to memorize formulas in this chapter. I'm going to look for some formulas that might help me here. What is AT? Well, here it is. Little at, the way I told you, what I told you at was, it's the tangential component of acceleration, and what it was it's a dot t. That means I gotta go find capital T, the unit tangent vector. Maybe I don't want to do all that work here. So there's another, I'm looking in the book goes on here. They say it's v dot a over the magnitude of v. V dot a over the magnitude of v. By the way, that's the same thing, I guess. I should have known that. They also call that d squared s over dt squared. Well, what about an? An, they say, is a dot n. Okay. I feel like I don't want to go find n. I don't want to go find n. So what can I do instead? I could do v cross a over the magnitude of v. V cross a over the magnitude of v. They also say it's the magnitude of a squared minus at squared square rooted. This might be cool. This is like Pythagorean theorem. It's the magnitude of a squared minus little at squared. That's an. Well, I'm going to do something. What am I going to do? I might just try this. Do I have V? Do I have A? I do have V and A, right? This is V. This is A, right? All right, I'm going to try this. I'm going to try V dot A. What's V dot A? It should be pretty easy. V dot A. V dot A. 0.
64t.
Well, you're adding, you're multiplying. 32 times 32. What'd you call it?
Right.
What's 1024?
1024t. That's V dot A. 1024t. All over the magnitude of V. Where's the magnitude of V? Well, there's V. What's the magnitude of that? Square root of 880 squared plus 1024 t squared, I guess. Magnitude of v. Well, that wasn't too hard. There's AT in general at any time. That's the tangential component of acceleration for this bomb at any moment. Whew. I mean, we developed a formula for it. And it doesn't clean up much more than that. Check this out. I'm going to try this AN, and I'm going to try this formula right here. Here it is. Here's AN. It's the square root of the magnitude of A squared. Now tell me, what's the magnitude of A?
1020.
Well, what's the magnitude of A?
32.
32. Yep. And if it's squared, it's 1024. Or, yeah. Minus this AT, which is this thing. Wait a minute. Squared. This thing's squared. Oh my God. That means the numerator is squared. Oh my God. That means that's squared and that's squared. Oh my God. The denominator is squared, which, oh my God. That means I could get a common denominator and get this together. Oh my God. That would be this. That's my denominator. That's my common denominator. What do I have to do? That means I got to multiply him by 1024. So he'll be 1024 squared t squared minus this 1024 squared t squared. I think those will cancel. I think I'll get, I think my numerator is 880 times 32. It's the square root of 1024 times 880 squared. Dude, I just did a lot of work in my head. But I think I'm kind of happy. Kind of happy, not super happy. Just kind of happy. I don't know. I'm exploring problems. You guys should explore some problems. We need to quit today, though. It's 12:15.